Okay. You can have in this a derivative ontology. So, as I say, if the fundamental ontology were, say, electrons and quarks and so on, but you say, gee, there's, in a certain sense, lots of things in the world that we may want to talk about that are not individual quarks and electrons, but they're somehow compositions of them or derivative from them, that's fine. You can define and explicate these derivative things. You'll see an example. I mean, this is kind of abstract, but you'll see the example I'm going to give. And you should say how the derivative ontology derives, presumably by a mathematical function from the fundamental, well, the representation of the fundamental ontology. And you can talk also, and this will be relevant for our topic here, about mathematical pseudo-entities. They're pieces of the mathematics that don't represent anything physical at all, although if you weren't being careful, you might trick yourself into thinking that they do, and you might explain what they are, why they're useful for some calculational purposes, and so on. Okay, so that's the way I think a proper physical theory should be presented. So there's a proper, more or less proper physical theory we've all seen. You can work your way backwards from the laws to the fundamental ontology, because what I said was that the laws should only mention things that are in the fundamental ontology. So if this were in canonical form, this would be okay. You could just stare at those and say, classical electromagnetic theory, what is it? Well, here are the laws, and then I can sort of analyze those and figure out what it is in a certain way that this theory is committing itself to physically. Everybody's seen this. Now, one other thing this is going to do, as we'll see, is it's going to make you reflect in ways you maybe haven't before. When you start thinking about this question, how does the mathematics represent the physics? How does that relation go? Certain questions jump out at you. All of this stuff, actually, I'm talking about today, I've never talked about this before. Well, I did a couple weeks ago, but basically I did all this work in the last 6 weeks because for the first time I was teaching a course on gauge theory, and we were just starting out with classical electromagnetic theory, and it's the first time I taught it. And everybody knows you think you understand something until you have to teach it. And then all of a sudden, like all of these huge gaping holes of ignorance that you have jump out at you, because you say, but what if the student asked that? And you say, yeah, well, that's a good question, right? All these questions came up, and this is the result of that. All right. So what would the fundamental ontology be if I took Maxwell's equations in this canonical form, which is due to Heaviside? Apparently there were 20, Maxwell wrote down 20 equations, 12 of which aren't even considered part of electromagnetic theory anymore. And it was Heaviside and some other people who gave it that canonical form. And notice, and we'll talk about this too, that canonical form is written in a mathematical formalism. And you have to think, how is that formalism working? All right. So if we take those to be the nomology of the theory in canonical form, then we can just read off the mathematical representations of the fundamental ontology. And what we would get is that there is something we call the electric field that is represented by this vector field E. There is something called the magnetic field, which is represented by this vector field B. There is a charge density that's represented by a scalar field rho. There is a current density represented by a vector field J. There is a time structure that's represented by the T, and there is a spatial structure that's represented by the vector R. And that's what we have in that particular. Now, that's just Maxwell's equations. To really finish this off, as we'll see, you need like the Lorentz force law and Newton's equations. And we're going to throw those in at the end, but right now I'm just focusing on electromagnetism. Okay? So if I just stare at the mathematics, and I know at least this much about the mathematical formalism, that those are the fundamental physical things this theory is about, the math will suggest things to me, right? That is, it'll be very natural to read the mathematics as telling me something about these physical items. And in a well-chosen mathematical representation, and you can have the same theory, what we would normally say is exactly the same theory presented in different mathematical guises, as we know. You can change the mathematical language. And each of these mathematical languages will be suggestive of a certain understanding of what the physical world that's being represented is like. And one thing that's sometimes very useful to do is just to think, can I restate this theory in another language? Can I restate it in yet another mathematical language? Can I, and this is something else I've been doing for the last 5 weeks, invent a brand new mathematical language? I won't take you into that. A brand new mathematical language to present the same theory, because they will give you different suggestions about what the world might be like. The mathematical language being used here is vector calculus. And basically, we have two gadgets for representing physical things: scalar fields and vector fields. And we represent the vector fields with the bold. And so you might think, well, that duality of the mathematical apparatus is reflecting a kind of duality in the physical world. There are physical things that are scalar. Again, now you see, you hear now the ambiguity of scalar field, right? There are physical things that are scalar fields, meaning what? Meaning there are physical things that at each point in space-time have one physical degree of freedom. And so just by handing you a single number, if that's an appropriately calibrated number, I can nail down what that degree of freedom is. And there are vector fields that somehow have 3 degrees of freedom at every point, and I often visualize that in terms of pointy arrows, right? That I can't just give you a magnitude, I have to give you a direction. You can think of the 3 numbers as one of them giving you the magnitude and the other 2 giving you angular directions. So then the vector fields look like little pointy arrows in your head. There's this use of the cross product. Now, this is all going to seem like really weird. Why am I talking about this? This will be clear in a second. There's the use when you actually write down the equations of this cross product, and you would say, okay, if I need the cross product to write down the laws, I guess the laws should only make sense, or the quantities that I need to talk about to use that should only make sense in a setting where the cross product itself, in some sense, makes sense. Why the cross product? Well, because we've got curls, right? When you write down Maxwell's equation, you have to talk about the curl, and you have to talk about the divergence of your vector fields. And the way we represent the curl in this notation is by a cross product with nabla. So you then might ask yourself, well, what's that all about? What's this mathematics telling me? What is the, I have a vector field, and now I want to talk about the curl of it. What is that, right? And I want to talk about, so this is something that, again, maybe everybody in this room has figured this out. I hadn't figured it out. And the word curl or roticity, you have this image in your head of a vector field as a bunch of arrows, right, in space pointing some way, and you say, okay, the curl is somehow telling me how curly they are, right? How much they somehow are rotating, or if they have nice flow lines, right? If I integrate through and get flow lines, the curl is a measure of how much those flow lines are twisting and curling. Then you also have that's sort of one question. Another is, what is this deal with this cross product that I'm using? Right? It's important in the statement of the nomology. Again, we have the same question. We've got the same nabla dotted into E and B. What do I mean by the divergence of a vector field? Right? What does that represent? And normally, with the divergence, just the way you think of the curl as somehow telling you about the twistiness of these arrows, you think of the divergence as telling you about sources and sinks, right? So if all the arrows are pointing into a region, or better, if all the arrows are pointing out of a region, it's got a divergence. That means there's a source. You know, if you think of the arrows as the flow of water, it means there's a source there. And if more arrows are going in than going out, you have a sink, and you have a convergence rather than a divergence. So you have a sort of a picture in your head of what the math is about. Now, there's something weird about the curl. Right? There's something a little surprising about the curl itself, and then there's something even more surprising about the way we represent the curl. So let me just go. This is going to strike you as, I probably already think I'm crazy. But I want you to get in the mood of noticing little tiny things that you never noticed before. At least I never noticed before, because you learn them so early. And you learn them by rote, when you're just beginning to learn mathematics and just beginning to learn physics, and your job is not to question anything, but just to suck it all in and spit it out on the tests, that you get used to it and you don't sort of think about, what does it mean? So what's weird about the curl? Let me try and convince you there's something a little weird about the curl. So, as I say, in the Heaviside representation, we define the curl as the cross product of nabla with a vector field. And that gives us yet another vector field. So it's a kind of operation. So this is actually where I began when I was teaching this stuff. I said, let's just think about these operations. What does the gradient do? Okay, it takes in a scalar field and it spits out a vector field. And what does the divergence do? It takes in a vector field and it spits out a scalar field. What does the curl do? It takes in a vector field and spits out a vector field, right? But when you learn, everybody knows when you learn how to take cross products, you learn the right-hand rule, which, again, probably everybody thought it was a little weird, right? What's special about my right hand? So there was something strange about that. But there's something even much more strange about it, about this mathematical representation. So let's first talk about what the curl is physically if I think of the vector field as a representation, natural representation of something physical, which is what I'm using this math for. So if you think of the curl or the roticity of the field as talking about the twistiness of the field of the field and of the integral curves, you'd say, can a field with perfectly straight parallel flow lines have a curl? And your natural reaction is, no, of course not. The curl measures the twistiness. And if all of these flow lines are absolutely dead straight and parallel, nothing's twisting, it can't have a curl.